So first of all, good evening, everyone. Of course, special welcome to you, Al. Thank you for willing to talk to us and answering the many questions that the people here have. Yeah, so I've been getting a lot of questions, like 4 or 5 A4 questions for you. So I'm just going to start with you. Can you quickly tell me who you are or what you've been doing?
Sure. I'm Allen Chen. Obviously, I work for JPL, which is one of the NASA field centers. We typically have led a lot of the Mars missions. I joined JPL back in 2002 and got started working on a project called, back then called Mars Smart Lander, which eventually became Mars Science Laboratory and delivered the Curiosity rover back in 2012. So I worked on the entry, descent, and landing system for that. For those 10 years to get it to landing, and then turned around and got on the merry-go-round again with the Mars 2020 mission, which delivered the Perseverance rover and Ingenuity helicopter this past February. So a lot of time spent trying to get about 14 minutes to go right on Mars.
So you spent most of your time for those 14 minutes, the critical minutes, and now Perseverance has landed about, what is it now, half a year ago, slightly less than half a year ago. So what have you and your team been up to recently?
The team's kind of gone on to a lot of different things. One thing that's still keeping us together is doing some reconstruction. One thing that we always want to do is make sure we understand what just happened with the landing, whether it goes well or poorly. In this case, it was the good version, which means we had a lot more data to look at to understand how our system performed versus what we expected to, what went right, what didn't go right. And we're trying to write that all up to make sure that we preserve that knowledge for the future so that future work can lean on that and learn from both our mistakes and the things that worked right. But beyond that, the team has started to disperse onto other projects and begin to work some new missions as well. So lots of people going off to do lots of new fun things.
So it's not the same team that did Curiosity that did Perseverance. It's a completely new team.
It's a mixture, right? Certainly there are folks like me who were carried over from Curiosity and brought a lot of the knowledge of what we did on Curiosity to Perseverance, which was particularly important because the Mars 2020 project, in many cases, that you can tell kind of from looking at it from the outside, was based a lot on the heritage, the work that we did on Curiosity. So having that information and trapped in people, in the wetware of the brains of people like me, is kind of useful, but it also is extremely helpful to bring in new folks to let them understand what's going on and to ask new questions about what we're doing and bring that kind of youthful energy as well to do things. So it was a good opportunity to mix both new and old folks.
So as you said, you've been looking already into the flight of Perseverance now. Are there already any updates? Did everything work as planned? Mainly the parachute system, but of course the entire EDL system.
Yeah, so far so good. There's been a few surprises, but not too many huge mistakes or whatnot. Let me. I can actually show you. I don't know how many of you are part of the International Planetary Probe Workshop community, but we're actually doing a session on this tomorrow. Talking about the detailed performance of, so a little plug for that. And it's free this year. You don't actually have to travel. You can all do it from your guest bedroom like me.
Sure.
Yeah, we're talking tomorrow morning actually, and we'll show talk about the, pretty quick rundown of how we did overall. But I can give you a sneak preview if you're interested in that.
Oh, that would be great.
Let me see if I can figure out how to share everything let me try to give you the one slide version of this if that works. So how do we do? You can see this, right? I've lost my video.
Your thing.
Okay, good. Many of you have probably seen our entry, descent, and landing timeline and of how we expected events to go throughout EDL through that 7 minutes of terror, as it were. This is kind of the one-stop shop for how we did versus predictions. Things that were as predicted or what we're considering within 1 sigma of our prediction are in green. Things that are a little bit more, 1 to 2 sigma, are in yellow, and things that surprised us are in red. So the good news is you don't see very much red on here, except for the parachute, the parachute image itself. The only thing that really surprised us was that the peak deceleration was a little bit lower than we expected, actually quite a bit lower. And I think we figured out what's going on there, in that the upper atmosphere was different than we expected. And there was a sensitivity in the vehicle that we didn't completely understand, even after all this time. But of course, that's not really much of a big deal for a guided entry system. We got to where we needed to go. There's a lot of green on here. The timeline, in terms of when we expected events to occur, pretty much we nailed it. Things were right as we expected. There was 1 second less of terror. It only took us 6 minutes and 59 seconds to get to the ground. But I don't know, still felt like a long time to me. But otherwise, we did pretty well. A couple of other yellows on here are kind of sort of expected. The fuel usage, you might notice that we actually used less fuel than we expected. That's not necessarily surprising. Our simulations in general are geared toward trying to be conservative about how much fuel we use. So that was on the low side of what we expected. What else can I tell you? Otherwise, the altitudes that you see there in yellow were actually a little bit higher, just a hair higher than we expected, 1 to 2 sigma higher. Again, related to what we believe was the upper atmosphere being more dense than we expected. So this is kind of the one-stop shop for how we did. The short version is pretty well. In terms of where we landed, things went pretty well there too, though it's not clear, since you guys are all parachute people. Let me focus a little bit there on how much of it was parachute related. Because we have range trigger, sorry, by the way, I don't know how much you all know about our EDL system. Let me know if I need to go back and explain our system to you all. But we have this range trigger, which allows us to deploy the parachute based on navigated range, how far we've traveled from the entry point. Think about it that way. So after that point, we pretty much have used that trigger to crush all of the uncertainties that are left over from guided entry. So our error was pretty much nothing at the time we deployed the parachute. So anything that causes us to not be on target at that point pretty much has to do with the winds, what's going on with the winds at Mars, or what the parachute itself is doing. As I'm sure many of you are aware, the parachute can act like a sail, and it's sort of semi-chaotic in the way it trims. It can kind of jump around from different trim points and take you for a ride while you're on parachute. But it's difficult for us to understand how much of the movement here. You see that we landed about, or the parachute, we should say we were done with the parachute and separated from the parachute about 1.05 sigma beyond our target. About 1.6 or so kilometers from the target that we had aimed at. We don't know how much of that is due to the winds versus the parachute trimming. So that's part of the mysteries that we'll endure. We're trying to do our best to try to figure that out. But there's really not a lot of information you can use to know really whether it was the winds blowing you there, or just being higher up at parachute deploy, or the parachute trimming and taking us for a ride. But in general, it's not bad, right? We went pretty far and only missed by about 1.5 kilometers in terms of where we're going. So, or 1.1 kilometers at this point, and then another 0.5 kilometer we added from the TRN, the train relative navigation divert. That was a lot of stuff there. Again, I'm not sure exactly what you guys know about DDL or not in our system. So I'm happy to go back and explain that in more detail if you'd like, but that's kind of the short version of how we did. Was pretty darn good.
Yeah, and especially for a 6-month flight, 1 kilometer is quite spot on.
Yeah.
You already mentioned it, the bit of terrain relative navigation and then range trigger. Those were new things for Perseverance. Mm-hmm. One of the questions I got was how did you guys come to the conclusion that this needed to be implemented? And are there or were there backup systems? So when the system would freak out during flight?
Yeah, those are great questions. The range trigger was an idea actually that's been a long time in the making. We actually were toying with it back on Curiosity with the idea of trying to use it there. And I think our flight, it was kind of one thing too many, if you will. There was a lot of new stuff for Curiosity when we designed that system. Between landing obviously really big rover, new Skycrane system, new guided entry, new heat shield, whatever, right? There was a new parachute. There's so much new that we didn't want to stack one more thing on. But at this point, we kind of reached the conclusion that we were a little bit more confident in what we'd done with Curiosity to be able to take that next step with Perseverance. But more than that, the picture I just showed you, in some sense, the place that we've gone is the reason why range trigger and terrain relative navigation are part of the mission. The places that we want to go to, right? That in terms of, I shouldn't say we, I should say that the science community, in terms of trying to go to places that have evidence of past life, they want to go to rugged places, right? They see cliffs, they see, you know, the layers of cliffs. You think about the Grand Canyon. I don't know what the European equivalent of the Grand Canyon is, but you know, places where you have access to a lot of history, and places where, you know, that are not flat and boring, right? And that's kind of the opposite of what folks like me that want to land are looking for. I'm looking for parking lots or runways, right? Flat, boring places that have no rocks, no cliffs, none of that. That's, you know, it's not like a guy flying his plane wants to land on a cliff face or anything like that. Same for us, right, when going to Mars. So there's that natural conflict, right, that they see all these beautiful science targets and I see death all over the place for our mission. But you know, that's kind of what drove us to add these extra capabilities to Mars 2020 since Curiosity, because range trigger really allows us to shrink the area that we're going to. Our kind of final targeting landing ellipse on Curiosity was 20 kilometers long, whereas for us here on 20 kilometers long and 7 kilometers wide. Our final targeting ellipse here for Perseverance was only about 7 kilometers long and 5.5 kilometers wide. So we can land in a much tighter spot. And then, of course, we don't want that entire spot to be a boring runway if the scientists have anything to say about it. And if you look at our landing site, it's not, right? We have this 60 to 80 meter cliff running through the middle of it. You can see where the rover landed, surrounded by death all around it. There's rock fields and dune fields and all those kind of things that we don't want to get into. So that's where terrain relative navigation really allows us to come into play, in that it can take that rugged area and look for the flat spots nearby to land in. So suddenly we don't need the entire 7.5 or 7 kilometer by 5 kilometer long area to be a runway. It can be full of bad stuff as long as there are little tiny runways interspersed within there that we can reach. And we can take that to the next natural extension, of course, right? One of the things that Perseverance was limited by was the amount of fuel that Curiosity flew, because we flew literally the dynamic test model descent stage from Curiosity. We refurbished this piece of hardware and turned it into a flight descent stage. So that capped the amount of fuel we had, 400 kilos of fuel. It's possible, very possible, that future missions will take more fuel and use our TRN capability and say, I want to land right here. We're going to do pinpoint landing. Forget looking for all these little tiny parking lots nearby. We're going to bring enough fuel to make sure we can fly all the way to that one spot that we want to go to. So we're looking at that. So it's kind of this incremental development. But that's a long way of saying the scientists made us do it, right? That they're trying to take us to sites that, and really we want to do this too, right? Because the whole mission is really, I'm kind of being a little bit flippant about it, but yeah, that we are all in this together. We want to give our chance, take our chance at finding the best possible evidence of past life. Nobody wants to spend 10, 20 years of their life coming up with nothing. So putting those capabilities on was a big deal. And more than that, we saw this coming, right? The TRN didn't just appear on Perseverance. We've been developing this technology for 20 years, since back in the actually right after Pathfinder days. And it has a little bit of a cousin in the DIME system, Descent Image Motion Estimation System, that was on the Mars exploration rovers, where they took a couple of images with their engineering cameras on the way down, fired these little solid rocket motors to try to kill off some horizontal velocity. The feature tracking system from there is kind of buried within our terrain relative navigation system. So, some people joke there's nothing new, right? And in some sense, there's nothing new because you spend the time working in parallel to make sure that by the time you need it, you have what you need.
So even though it was the first time the system flew, it has been flight tested in the last 20 years already.
That's right, in some sense, right? Obviously, we did a lot more with it, but the technology development program took us to a field test of that system out in the desert under a helicopter, much like we eventually did with something closer to the flight unit, but with a prototype unit back in 2014, right, in the very early days of the Mars 2020 project. And that wouldn't have been possible without the investment in the technology development side of things. So quick plug for technology development, as long as you can keep it relevant to what you're trying to do. It can really pay off if you can then suck it into the flight missions at the right time.
So, and I'm going to assume that you have all this navigation capabilities, and the Skycrane ties into that, giving you the control to also avoid these obstacles.
That's right.
One thing that the team has joked about for the last couple of years is that meeting where somebody proposed this Skycrane. How did that go?
Yeah,
so the first time someone tells you it's the science fiction.
Yeah, it's interesting, right? So I can tell you that story, right? Because I was there. This rewind back to I think 2003. I even remember where I don't know how many of you were born then. This is making me feel really old, but you were all toddlers or something. I remember how that went down. There were about 13 of us there. So you got to kind of remember the context of where we are a little bit at that time in 2003. We're in the middle, actually, of this crazy trying to get the Mars exploration rovers to work. They landed in early 2004. And you got to look back to that system, right? Because there's a little bit of, there's a couple things going together. So I'll try to tell this tell this story in a way that kind of makes some sense. But first things first, right? The rover that we're trying to land, even back then, is several times larger than the rovers we've landed before, right? Curiosity ended up being 900 kilos, 899 kilos. And the Spirit and Opportunity rovers were about 170 kilos each. So, on the order of 5 times heavier. And understand where we were mentally at that time. We were tearing up airbags all over the place. Right, we were trying to test the airbags for this 170 kilo rover and ripping them to shreds. We had reached the limit of what we could do with airbags, and weren't honestly sure that, I think we had some confidence that Spirit and Opportunity were going to make it, but there's fear there, right? That you encounter the wrong rock and that you stroke out. We're gonna tear the airbags or stroke them out. We knew that we had reached the limit. That airbags were not going to do it anymore for us. So we had to come up with something different. We had to either be going a lot slower when we dropped the rover on airbags or do something different. So if you're going a lot slower already, right, if you have to slow down much more than what we did on Spirit and Opportunity, can you push it the extra mile and not use airbags at all by controlling that slowness and slow down even more? And really touch down so slowly that you don't need the airbag system. It's kind of the thinking, right? Okay, airbags, we can hit hard, but now we can't use the airbags anymore because we've reached the material limits of the airbags and our rover's gotten so heavy. So we need to slow down. But wait, if we slow down so much that we have reduced the need for the airbags, can we slow down even more so that we don't need the airbags at all? That's kind of the thinking that got us there. And then thinking, hey, we're building a big freaking rover here. Not just we don't have to build this very protected rover. It's going to be big and have lots of ground clearance and big wheels and big mobility system. It's already designed to interface with the ground, to touch down on the ground and drive over it and fall off rocks when we're slipping off big rocks and all that. Can we just use that instead? If we can slow down enough that we can bring ourselves into the design envelope that the rover had to be designed for anyway, to drive around on Mars, then we can eliminate an entire system, right? We don't need an extra kind of shock absorber system. That's the thinking. So it's kind of the linchpin that got us there. Now, on top of that, let me now string us back to, okay, we got to touching down slowly. Now we touch back to how we got to Skycrane. If you think that connecting 2 vehicles by soft goods is terrible, what do you think about 3? Because that's what we had on Pathfinder and Spirit and Opportunity. If you think about this 3-body system, I don't have a picture handy, but many of you probably have in your brain, right? We got this parachute attached to this back shell, which below it is hanging this lander with the airbag system. We have this 3-body system with things connected to each other. So we had 3. If we cut down to 2, how simple would that be, right? That'd be much simpler, right? So maybe a little bit, flippant in that sense too, but that was a very difficult problem, right? Connecting all these soft goods together and trying to control that 3-body system. Maybe we were, we're nothing if not arrogant here at JPL, but it was kind of a situation where we thought we had solved that soft good connection problem, and that problem was worse. So how broad could this one be? So put those things together. Touch down slowly because it's so heavy. Landing gear that we already have because we have to drive around on Mars with this big freaking rover, and then some confidence in our ability to connect things with soft goods, kind of put that all together. And that allows us to understand, like, the linchpins of those are the ability to really control our vehicle precisely and touch down slowly. And that's where kind of the hidden pieces in our system that we're really dependent on are high fidelity or high accuracy ability to detect our altitude and velocity. That's where our radar comes into play. And then high precision ability to control the vehicle. And that's where those the throttleable engines that we had on the descent stage for both Perseverance and Curiosity come into play. So that's kind of the long version, I guess, of the Skycrane genesis. And of course, I could extol the virtues of the Skycrane even more. But that's kind of the how we got there from here.
So it was almost kind of a natural. It evolved naturally.
That's right. I think that again, back into the whole "there are no new ideas" thinking, right? That it's not like this was birthed from somebody's brain, whole cloth, right? It didn't just come out all together. It was a bunch of ideas whose time had kind of come, and it just took a brainstorming sessions to kind of gel it all together.
So I can imagine. So Perseverance launched somewhere end 2020. How often did you wake up at night dreaming of all the possible things that could go wrong?
Yeah, a lot. I mean, I think that I don't know if it shows up very well on Zoom, but I've got a lot of patchy gray hair, more than I probably ought to have for my age. So, I think it takes something out of you, I'd say. I won't lie about that, right? There's a lot of stress.
It's a high risk, but also high reward kind of setting.
Yeah, exactly.
And are there things that you and your team did or could still do during transit? I mean, I'm just going to assume on simulation and software side, there's still quite a lot of work that you can do.
Yes.
Are there things?
Well, actually, for the first time, I think ever for our Mars missions, we actually landed on the software that we launched with. Usually, we launch and then change the software in flight because we either didn't finish it before launch or found fatal flaws with it or whatnot. And for the first time, we didn't have to do that this time. We actually landed with what we launched with, which was great. But there's some, we didn't just slack off during that time. There was a lot to learn about the vehicle on the way there and to check it out. We need to check out all the EDL systems on it to make sure that everything was working. So we did a lot of checkouts on the way. There were anomalies on the vehicle itself. It was not the smoothest cruise we've ever had. There were problems that we had to solve on the way there. Not EDL specific problems, but problems that could impact EDL as well, including things like we were seeing a lot of single event functional interrupts on our processor. So we were trying to figure out what to do with that. And of course, that plays in very, very keenly in that last few days, that final approach period, where we're trying to put the vehicle right on target and give it the parameter updates that it needs to succeed. We wanted to be able to respond quickly if something bad happened to the vehicle in the last few days as well. But that actually all went very well. In fact, the last maneuver we did on the vehicle during cruise was in December. We actually, I think on December 20th or so, I think was the last maneuver we did, which is kind of unheard of, actually. We managed to target the entry point so well at that point that we knew we had guided entry to finish the job, and we're comfortable with that. So we practiced always, doing last minute maneuvers if we needed to save the mission or put us more on target, but didn't have to do that.
Okay, as is one of the questions indeed that I got several times with you. You and your team are there in mission control, but it takes quite some time for the data to come in. So on the actual landing phase, there's nothing you can do when you see that it goes wrong. So the last minute changes, that's the thing that you reverse then.
Yeah, we certainly rehearsed the last few days because it's a dance of should we do a maneuver, should we do a parameter update based on what we're learning. I think the key is that we don't really know where we are relative to Mars until late in the game, until a few days out. We have a better understanding then of the vehicle's trajectory. And in fact, we really know in the last few hours as Mars's gravity starts to kind of reshape our trajectory as we're getting closer. You can see something that you don't see before. So there's an opportunity to do things there. But we're worried about other things. Like we saw a lot of single event functional interrupts during flight that could cause processor resets or cause delayed eggs in terms of memory faults, basically on the way down, that can cause you to lose the vehicle. So we wanted to be ready to respond to those quickly if necessary.
Okay. I want to go back a bit to between Curiosity and Perseverance. So Curiosity landed, I just looked up the year, I forgot already.
2012.
2012?
I have a visual reminder that actually my third son was born a couple months after Curiosity landed, so it's about 8 years ago. 8.5 years ago.
Good. And between Curiosity and Perseverance, you had the infamous LDSD mission and the ASPIRE flight. Mm-hmm. Can you elaborate a bit on why ASPIRE at some point happened and what you learned from those missions and how they were implemented in Perseverance? Yeah,
absolutely. You know, probably some of you know this story a little bit, but one of the things that we didn't want to change between Curiosity and Perseverance was the parachute. Parachute worked great on Perseverance. It looked good. You know, we didn't have a lot of, we didn't have the EDL camera data that we had this time with video of it or anything, but, you know, it looked good from MRO and provided the drag we expected. So the parachute was one of the things we think, that was tough development for Curiosity, but shouldn't be a problem for Perseverance. We don't have to do anything to it. It's all good. So in the meantime, right, in terms of, you know, I talked a little bit about technology programs moving in parallel. To eventually produce something that you might need in the future. The Low Density Supersonic Decelerators project, which is LDST that you mentioned, was off trying to develop aero decelerators for the future, for landing things that were much bigger than Curiosity or Perseverance. They were looking at developing aerodynamic decelerators like balloons, inflatables that kind of make your aeroshell bigger later in the game to give you more drag area. Or the thing I really wanted, which I still really want, is a really big supersonic parachute, right? We've gone to 21.5 meters, but could we go bigger? Could you give me a 30-meter chute or a 33-meter chute? Imagine what we could land if we had something that big, and a supersonic chute that was that good. So the LDST project went off and developed a bunch of these things, also a balloon, which is a different kind of decelerator, kind of an inflatable that trails behind you instead of one that goes around the aeroshell like a balloon. Like the SIAD, supersonic inflatable aerodynamic accelerator. But I was most interested in the parachute, and they went off and designed a parachute, different design than the MSL or Curiosity parachute. MSL Curiosity and Perseverance use a disc gap band parachute, much like the Chinese just used, and Viking just used, and everybody else has used pretty much in between. This disc gap band, but they wanted to design something different for reasons that I won't go into. So they looked at a disc sail and a ring sail and tried to develop 30-meter chutes and went off to Hawaii and spent a long time in Kauai at the Pacific Test Range, launching things on balloons, then firing them up to supersonic speeds, and then doing their inflatables, and then deploying the parachute. So early in the Mars 2020 project, we were just interested observers, right? Didn't really care much, but they designed the parachute using the same kind of tools analytically and approach that we use to design the parachutes and size the parachutes for our Mars missions, whether it's Curiosity or Perseverance in those times, or MER or Phoenix, right? We always use the same approach and use subsonic testing of it first. And that's what LDSD did too. They used that same design approach, did subsonic testing, showed that it worked, that the parachutes for the most part did their thing, and then took it up to supersonic conditions up out over the Pacific, west of Kauai, and blew up those chutes. The parachutes turned into confetti cannons. It was a mess. I could show you pictures and video, but that's the stuff of nightmares for parachute folks, right? Like really big time, just parachute disappears very quickly, and you see bits. And what we recovered was bits in a tangled mess. So that really gave us some pause, right? Like, hey, we just designed a big parachute the way that we designed things for Mars, and it didn't work. What happened, right? We tested the way that we tested subsonically. The thing that we hadn't been doing since Viking was supersonic testing. What's going on? What don't we understand, right? That was the problem. Have we just been getting lucky this whole time? And do we want to take that chance that even though it worked great for Curiosity, we designed something else the same way and busted it? How lucky do we feel? Can we just use that Curiosity chute again or not? That was a real question for us. So that's what kind of launched us into the ASPIRE program. It was okay, this is the beginning of sample return. This is a $2 billion mission. We do not want to take chances here. Maybe we've been walking too close to the edge, right? The cliff has always been there, and we're just getting closer to it, and haven't realized that we were about to step off it, and we're sitting on that knife's edge. So let's do this ASPIRE campaign to prove that we aren't there, and more than that, let's make sure that we're not there by beefing up the parachute. So that's kind of the thing. We try to understand where to beef up that parachute to make it stronger, to make it more resistant to the type of thing we saw on LDSD. And then given that subsonic testing was not enough to show us the problems in those LDSD chutes, we developed the ASPIRE program to go ahead and take them up to supersonic conditions again to prove that these chutes would work. So that's what this was about. By the way, do I think the Curiosity chute probably still would have worked for Perseverance? I think there's a good chance. We decided it wasn't worth just trying to use the build to print chute from Curiosity and testing it in the ASPIRE program. We'd rather build a strengthened parachute and take it up to higher conditions to prove it and feel better about it. But yeah, I guess we'll never know, because we went with the more conservative approach.
Is the build to print parachutes, they did survive during ASPIRE, correct?
It did during the first test. We didn't take it to the full load, right? We took it to MSL-like loads, and it did survive that. We didn't take it up to the flight limit load, up near 50,000 pounds. So you're correct. We did fly one build to print chute, and it did survive, but we didn't take it to the higher conditions.
And then you took both the strengthened parachute and the kind of new information as a double safety.
That's right, exactly. It's kind of the belt and suspenders approach, right? We knew it worked in supersonic tests, and now we also know that it worked in that we have the stronger parachute that's inherently stronger to handle some of those things.
So for future Mars missions, have the simulation tools / methods of verification validations been modified based on these learnings, or will you still use the same?
There's a few things that we've done we continue to build upon what we're doing. I think I'm hesitant to say too much here, because the parachute itself, I think in the end is always maybe we'll get there someday, but it is an empirical device, right? It works because we show that it works. Right, the people who maybe some of you are working on fluid structure interactions and trying to do that modeling of the chute, but that's a very chaotic event, right? On Earth, the chutes are inflating in 0.4 seconds. On Mars, it's 0.7 seconds or so. It happens very quickly, and it's pretty chaotic. I think that our ability to model that is always going to be in question, and our ability to get enough data to prove that the models are working, to validate those models, is also going to be in question. I think I have hope that we have a better understanding of what's going on, and our tools are getting better for analytically. But in the end, I think test is really what it's going to be about. And one good thing about the ASPIRE program in some sense is that it's given us the ability to do a reasonably costed test of supersonic parachutes. And in fact, that's what the sample retrieval lander, the mission that's going to go bring the Mars Ascent vehicle to Mars to pick up the samples that Perseverance is finding, is looking to do. They're already spinning up their own ASPIRE program to test it in an even bigger chute.
Yes, that was indeed going to be my next question. Will we see more ASPIRE-like flights? So the answer is then yes.
Yeah, I think it's very likely. Is
there a name for that mission?
Yeah, the mission is the Sample Retrieval Lander, SRL, is the follow-on to Mars 2020. Right now, they're just calling it the parachute development process of that, ASPIRE 2, for lack of a better name. But yeah, folks are already looking at that right now, and what we can do and test a bigger chute to higher loads, because that's what we think we might need, right? Trying to think a little bit to the future about what we're going to need.
Yeah, looking forward to it.
Yeah,
a good supersonic parachute inflation or a good sounding rocket flight is always nice.
Yeah, no, it's always good. It's confidence inspiring too to be able to do those things.
I had a question a bit more on the European side. So we looked at what NASA is doing. But hopefully soon, we have a Russian-European mission going that way as well.
Mm-hmm.
I was wondering if if there's any cooperation between NASA or JPL and, for instance, now ExoMars with the problems that are with the chutes.
There has been in the past. I have not been involved in much of it. I've just been aware of some of it. We were kind of busy until February of this year, a little distracted. But other folks at JPL were, right? We did some pole tests up on the Mesa here at JPL that you might have seen the video of. I think Issa released some of those video of those pole tests. I think the answers were sort of involved, but not very. We helped connect Issa with Airborne Systems, right? The company that built our parachute for Mars 2020, and I think they've been much more deeply involved. But for the most part, we've tried to answer when they call, but we're not in the driver's seat.
Not actively. And what do you think of the ExoMars EDL system? It's a fairly complex system with multiple parachutes and the pilot chutes on the main parachute.
Yeah, I mean, I don't know much about it in general, except having talked to some folks and read about it. Yeah, there's not one way to skin a cat, right? To be able to get to the surface of Mars. Does it look complicated to me? Absolutely, right? Do I fear soft goods? Every time. Even though I just told you how we're getting better at it, right? In terms of how we felt confident in Skycrane after a 3-body system. Parachutes scare me every time, right? Every time that you add another thing to the system that can go wrong. I'd much prefer things that are more analytical. And in general, the parachute is kind of the antithesis of what we're trying to do in general. We want to design things that are easier to verify and validate. In some ways, at a different time, I could make an argument that the Skycrane really is actually one of those things. And that's part of it. That's a lot easier to verify and validate that the performance of the Skycrane than it is for airbags. But parachutes are kind of the worst, right? That you're never going to convince me that analysis alone is going to be good enough to make a parachute system good to go.
Yeah, there will always be some kind of uncertainty for instance, I'm not sure if you know about his missions, such as Supermax. The mission that was flown on board Max's 9. We would compare to, for instance, an ASPIRE, a much smaller parachute, much lower cost. What do you think of missions such as these that are relatively lower mass, lower cost, lower size, but you might be able to fly them more often compared to full-scale testing? What are your thoughts on that?
I'm of different minds of different things, right? It depends what you're trying to do, right? That I think scale makes things different, right? There are things where scale models work, right? Aerodynamics of solid bodies like entry capsules. I think, the ballistic range testing we do of those things scales very well. But I think soft goods scale poorly in terms of how you want to do something. If you're, testing at full scale, I think is again, because it's a very empirical thing as opposed to an analytical thing. Once you change the scale, things are just wrong, I think. So if it's I'm a big proponent in this area of testing at full scale.
I see that Felix has risen his hand.
Yeah, question a bit on a slightly different topic. Now that Ingenuity has proven that powered flight is possible on Mars, do you think that will allow new types of recovery or entry, descent, and landing to be possible on Mars? More specifically, if maybe looking at parafoils to guide even closer to a landing site.
Maybe. I mean, we've looked at steerable parachutes and things like that in the past. The short version really is that there's just not much air, right? The density of Mars is very, very low. And that you just don't have a lot of time to affect a lot of change in that respect, unless you do something like have a helicopter or whatever, right? But but at least in terms of parafoils and all of that, we've looked at higher lift parachutes and all of that, and you're just falling too fast to, at least with landing big things, to get somewhere that's really helpful. But you're right. I mean, in some sense, right? I just got done telling you that all of our problems in terms of the growth of our landing lifts at this point, now that we have guided entry and range trigger, are all on parachute. That's when everything goes to shit, right? That everything was fine beforehand at parachute deploy, and then suddenly we've let go of control, and then you're at the whim of the parachute or the atmosphere to take us where you're going. So I understand the impulse, but I think in the end, there's just not a lot of control authority, even with a high lift chute.
Okay. And I also see two questions from Thomas Britting.
Yeah. I was wondering, maybe it's a question more for parachutes in general. On a technical point of view, what do you think that parachute systems or recovery systems can be improved upon in the near future? Is it more of a reliability thing, more parachute stability, looking into increasing the deployment envelope, or manufacturing maybe?
Yeah, I mean, I think, strictly with my blinders on, because I'm not seeing much past the sample return world. Things that as we get bigger chutes is a thing that we need at the supersonic speeds, which means huge loads. I mean, huge, right? If you thought that the loads on Perseverance, which were allowable up to about 50,000 pounds force in terms of our flight limit load, was good enough. We're talking a lot more than that for some of these bigger vehicles that we're thinking about. And that's got its own challenges, right? That suddenly we're talking about quite a bit more craziness. So that's where I'm looking right now. And how do we beef up this design and really also beef up the rest of the structure to handle that as well? That we build vehicles that can handle a lot of these loads, but suddenly they're usually about the same kind of loads that we see during entry as well. So the vehicle's kind of balanced in that sense. What's beginning to happen now is that the parachute loads are going to drive the system, that they're much bigger than the rest of the loads we're imparting in the system, whether it's through launch or through entry. So that transition is going to be painful, right? It's got people thinking about things like reefing parachutes, right, to try to control loads on the way. I'm not sure we're going to get there because it's another thing that can go wrong, but it's got us thinking about it because suddenly the design is so unbalanced now.
Yeah, that makes sense. Do you think that different types of parachutes could be a solution to this problem, like, for example, flying ring sails or disc sails?
Maybe. I mean, that was part of the thinking behind the big ring sail and the big disc sail that LDSD was working on, was that disc gap band chutes don't reef, basically, right? I mean, you can think about reefing, but it's kind of stupid. But ring sails and disc sails, yeah, right. That's kind of, those are chutes that do reef. We've seen them reef. That was the thinking along that line, is if we're going to build a big chute, let's build something that we can reef so that we can control the loads. But now we're scared, right? That what happened in LDSD? Was it just because the design sucked, or was it something else, right? We're concerned there now. So I think it's more likely that we're trying to just beef up the structure and deal with giant loads instead of trying to go to a different parachute design at this point, or try to reef, because I think it's we're afraid.
Yeah, future is scary.
Exactly.
And I see a question from Sebastian as well.
Yeah, a follow-up question. Then, if you see in the future that rovers get bigger and heavier, do you see that parachutes will become obsolete, or do you think that there's still a way that we could still use parachutes in some way?
I think at some point, right, as we're heading toward really big things, right, and I'm talking human-sized stuff, right, the stuff that humans going to need, that it's very possible that parachutes will become obsolete. That we're finally going to get around to supersonic retro propulsion, right? You don't hear much about it anymore, but right there, SpaceX had plans about Red Dragon and all that. They were supposed to have landed this year or whatever. But I think as we get bigger, you're going to at some point just ignore the atmosphere at that part of flight and just use big engines to get you to the ground. That's what I'm guessing is going to happen. So yeah, I think that we're living in the area that the parachute can take you to now, and maybe reaching the end of that. I'll probably eat my words, right? Everybody eats their words at some point when they say we're right at the edge of this and we're not going any further, right? But I think at some point, when we're talking, 5-10 metric tons or whatever, that people and their stuff want to land, then I don't think parachutes are likely to be a part of that. That's just my guess.
I guess we just have to see what happens.
Yeah.
You also had a question.
Yes, you mentioned the effect of wind earlier.
Mm-hmm.
Is that a major contribution? And just out of curiosity, is there any sort of data from orbiters that you can use, like a kind of weather report, or is it just based on empirical data?
No, great question. So the Wind is a major factor at that point, right? What's happening to us on chute. Now, by the way, major, right? Our landing ellipse is still only 7 kilometers long. So, you know, take that with and we're on chute for about 2 minutes. So, you know, think about 10 meter per second uncertainty for 2 minutes, right? You get a couple of kilometers there. And it can be more than that, right? Is the bottom line. And yes, do we have orbiters? Absolutely. And were we doing atmospheric monitoring all the way to landing? Absolutely. Do we have direct measurement of what we actually want to see? Absolutely not. You know, what we have is things like the Mars Climate Sounder, which is on board the Mars Reconnaissance Orbiter. So we can see the temperature structure, or temperature versus pressure, for the atmosphere, and then try to use that to infer wind speeds from that, which is very difficult, right? A little bit of temperature being wrong can give you a lot of wind being difference. So one thing that we do, of course, a lot of on Mars is modeling, and we do mesoscale modeling of Mars, which in some sense is a little bit easier than Earth, for better or worse, because there's no water, or at least not much water. So you don't have to worry about that so much. But a lot of it is is basically the forced heating of the terrain, and then what happens to as the terrain warms up over the course of the day, that diurnal cycle. And of course, Mars has a very repeatable pressure cycle across the year. So we have this whole activity both on Curiosity and Mars 2020 that we dubbed the Council of Atmosphere. So a joint atmospheric science and engineering team designed to try to characterize the Mars atmosphere for the things that we wanted to look at. And that was particularly density structure and wind structure. So those are the things we went after. How well did we do? I don't know. Right? I mean, were we wildly off? Probably not, based on where we ended up. But you know, can we observe the winds directly? No. We can observe the winds around the rover. Right? There's a weather station on both Curiosity and Phoenix, or sorry, Insight as well, and Perseverance. But that's the weather at 1 meter, and I don't care about the weather at 1 meter at all. We care about the weather at 10 kilometers, right? So between basically 2 and 10 kilometers or 2 and 20 is really where most of our action happens. So we can observe some things. By the way, MCS is just one option. We can also use radial occultation to understand the density of the atmosphere as well. And there's surface pressure measurements on Curiosity and Perseverance as well. Oh, and Insight as well. So we can get the total atmospheric mass as well. So that's those are all pieces of the puzzle. So it's better than nothing. It's a lot better than nothing, but it's not direct measurement of what we're after.
Okay. And yeah, you mentioned it briefly. Insight was, of course, a mission that landed between Curiosity and Perseverance. Were there things happening during, for instance, the Insight landing that changed Perseverance's design, or was that already too late, or was Insight such a smooth landing that?
Yeah, I mean, I think there wasn't much from Insight in particular that caused us much grief. We certainly looked at the reconstruction effort there. You know, the fact that they landed at the very edge of one of their landing ellipses was something that is not, we had to explain why that wasn't the thing that could happen to us. With Perseverance, and why our system was different. But you know, around the time frame was the Schiaparelli landing attempt as well. Yeah. You know, we took a hard look at that, right? There's a lot of truth to, you learn more from failures than from successes. I think there's a lot of truth to that. Now, what happened to them, of course, and I don't know if you guys know the details, right? But they ended up seeing higher on-chute rates than they had designed for in terms of the inertial measurements unit's ability to track those rates. And as a result, they saturated their inertial measurement unit and lost the ability to tell which way was up. That was basically, you know, the short version of what happened there. So that led us to take a look at a couple things. Well, for one, they asked us for help in understanding what happened in that failure. And since this is a parachute group, right, this is a very important thing, right? The parachute induces this oscillation underneath the parachute, which can be quite violent depending on how you design the vehicle, and was unfortunately too violent for Schiaparelli for a couple of reasons. So there were a couple of things that led us to look at. Number one, did we predict the modeling? You know, the way that we were modeling things predict what, you know, if we modeled the Schiaparelli setup, could we model what happened in terms of saturation? And the answer was yes. That the models that we had developed for Curiosity, actually, in this multi-body model, in terms of the supersonic deployment and what it does to the vehicle underneath it, did allow for rates that along the lines of what we saw in Schiaparelli. So given the geometry of how that parachute was set up and connected to the vehicle and the deployment conditions, the answer is yes, we could have seen this coming. Was this a problem for Mars 2020? The answer is no. Our vehicle is different in terms of how it's connected there. We allow for much higher possible rates. One of the things that Schiaparelli did, for reasons that I won't get into, was basically cut the resolution of their inertial measurement, or really reduce the saturation limit of their IMU by a factor of 2 versus what we did on Curiosity. So that made them more susceptible to saturating the IMU. Okay. So anyway, we discovered that what happened to them was predictable based on models, and that one thing they did made it worse for them than for us. That being said, that did give us some pause and give us some opportunity to go back over our problem alone and take a look at it as well. For one thing, nothing like flying it at Mars to understand your system, and so we had the Curiosity reconstruction data, and knew already at that point that the on-shoot rates we saw were a little bit above the mean of our model from Curiosity. So we actually tweaked our parachute model, our parachute multi-body model, to move the Curiosity experience to the mean. If you only have one data point, you move your model to center on that data point, I guess. So we did that. And second, it got us to look more carefully too, and we were already doing this, but look even more carefully at what happened on Curiosity in the reconstruction of the parachute deployment event. And one thing we saw is that we saw a little bit of a navigational error appear, not a saturation like what killed Schiaparelli, but a little bit of a blip during the parachute deployment event, both in acceleration and in angular rates. Not enough to cause us a problem. Sailed right through it and were able to integrate right through it. But a little bit of a hiccup. And what was causing that really was, you think of parachutes as being soft, right, and all the goods as being soft. But when you're using things like Vectran and other really stiff fabrics, things are really actually pretty hard, right? And they can cause a lot of shock. And there's a couple things in the system, right? Both the sabot reaching the sabot is what pushes out the parachute pack, and when it reaches the end of the net, it was putting a jolt into the system. And then also this confluence fitting, this piece of metal that kind of connects the triple bridle to the riser, kind of toward the bottom of the parachute train. But when that hit the end and you kind of stopped, that was providing quite a bit of a jolt to the system as well. And in fact, providing such a jolt that it was actually shaking the panel that the IMU was on the descent stage. And with Mars 2020, we were literally flying the same descent stage, so we should expect the same behavior. So although we didn't need to really do anything because the system, I think, was robust to it, we wanted to be sure that this problem did not bite us in the butt. So we did a few things. Since we're changing the parachute already, we tried to lightweight that chunk of metal, that the confluence fitting, and soften up the connection between that and the sabot netting and all that, and the rest of the vehicle. So that didn't provide such a jolt. It provided more of a kind of a more spread out jolt to the rest of the system. And on top of that, we divided the resolution of the IMU by a factor of 5. So we just raised the limit at which we would saturate, the angular rates at which we would saturate, by a factor of 5 to make sure that there was no way we would saturate on that. Reduced the accuracy a little bit of our attitude knowledge, but we had plenty of it anyway. But we wanted to be sure that we absolutely killed that problem, that we would not have a navigational error during the parachute deployment event that would cause us to lose our ability to know which way was up. So
no possible way that could happen.
That's right. So that's a long way of saying that you absolutely can learn from things that happen along the way, and there's nothing like trying to do something again to learn from that as well, and to try to make your system a little bit more robust. The gift of trying to do it again.
Yeah, I have one final question for you that I think we're sent 20 times. Most people here work in recovery team of theirs. Do you have any advice for them? Anything they should definitely not forget? And if they ever want to work on a Mars mission at NASA JPL, is that possible for them as a European?
Let's see. Let me try to pick apart all those different things. Let's see. Do I have any advice? I think your mileage may vary, right? I'm hesitant to give universal advice, right? Everyone's story is different, and everyone's experience is different, and things happen. I think they, be opportunistic, ask questions, be curious, and get involved, right? Those are things that I think are probably as close to universally applicable. But even then, right? I mean, everybody follows a different path, and I would be hard pressed to tell you to follow a path, because different people succeed through different paths. So, find your own way. In terms of working with us, I just got off a meeting this morning talking with ESA folks, actually, on the Earth return side of things. So we're already working together. In terms of working at JPL, it's a little tricky. In terms, we certainly do hire some foreign nationals, but it's rare in entry, descent, and landing stuff to work with foreign nationals. You can certainly work on the science side. We've worked with many folks in the UK and in France on atmosphere characterization, which we talked about earlier. The hard truth is, right, in terms of things that are more entry, descent, and landing directly applicable, that typically we need what are called US persons. So you either need to be a US citizen or a green card holder. So this is where I always joke that the International Planetary Probe Workshop should start a dating service or something, because you get a green card after marrying somebody. But I think in the end we can all work together, right? There's a tremendous amount of cooperation right now between NASA and ESA right now on the sample return campaign. So
go to ESSEC and join the European side of the sample return.
That's right. And certainly the other folks too, right? The Airbus is building the Earth Return Orbiter, which the Earth Entry Vehicle attaches to, right? And I always like to argue that the EDL problem starts well before EDL, right? That we're going to be holding on to that steering wheel with the ERO guys, with the ESOC guys earlier than when they push the separation button. So there's a lot to learn on both sides of this.
Sounds good. And I want to thank you so much for your time. We actually went through quite a significant part of the questions, more than I expected. Thank you for your answers. And we'll see you tomorrow at IPPW.
Sounds great. Hope I didn't bore the hell out of you.
We'll definitely be working. And I can only recommend the rest of you also sign up and watch the sessions. So thank you again.
All right.
And
no problem.
see you soon.
All right. Take care, guys.
Bye.